In the next part of this course, we're going to focus on different types of functions, but before we go there, we need to look at one particular special case that's not a function. Remember the function definition we talked about earlier. Each input must have one and only one output. When you're viewing a graph and trying to determine if it represents a function or not, there is a shortcut that you usually learn called the vertical line test. To apply the vertical line test to this circle, for instance, you imagine taking a vertical line, placing it across the graph in various locations, and if you can find even one place where it intersects the graph in more than one point, this would not be a function. So you can see I'm moving the black vertical line nearer to the graph, and when I stop and find a place where it intersects in 2 points, such as you're seeing here, immediately this cannot be a function. It should make sense to you that no matter how big or small the circle is, it will never be a function. Let's look at a couple other examples to make sure you have the idea. Here's a graph that's a parabola. I would take a vertical line and again move it across the graph, looking to see if I can put the vertical line in a location where it intersects the parabola more than once. Everywhere I choose to put the line, it does intersect the parabola only in one point, therefore this would be the graph of a function. Here's one last example, sort of a sideways parabola. As I move the vertical line across, you can quickly see I can find a location where I can place the vertical line and it intersects the graph in 2 points. As soon as that occurs, I know this is not a function. Now let's go back to the circle. You can see the equation that I've typed in to generate this graph on the left. This is the general form for a basic circle. The left side of the equation will always look like x squared plus y squared, and on the right-hand side you can have different numbers. To see what that number on the right is controlling, I'm going to turn on the other circle equations. The red circle has a 16 on the right side of its equation, and look at where it intersects the x and y axes at +4 and -4. The blue circle has 9 on the right-hand side. Notice it crosses the x and y axes at +3 or -3. And finally, when the right-hand side equals 4, you can see that the circle intersects the axes at +2 and -2. What we notice then is that the radius of each circle, measured from the center to the edge of the circle, ends up being squared when you put it on the right side of the equation. So if your circle is centered at the origin 0, 0, the equation will always look like x squared plus y squared equals the radius squared. Knowing that, where do you think the circle x squared plus y squared equals 11 will fall on this graph? 11 would be what the radius squared equals. So to figure out what the radius is, we need the opposite operation, the square root. The square root of 11 is a little bit more than 3, and you can see that is the radius of this circle, the distance from the center to the outside edge. And just to convince you, we can do this neat trick where instead of putting a number on the right, I just put r squared, and then by dragging the slider, I can choose different values for r, the radius, and notice the circle changes accordingly. So when the center of your circle is located at 0, 0 and has radius r, you can always get its equation by writing x squared plus y squared equals radius squared. Okay, so at the top of the screen you see the first circle equation we discussed, and then below it you can see I've entered a new equation, similar in format, but with the addition of these letters h and k being subtracted from the variables. Let's see what that does. Notice my sliders for h and for k are set at 0, giving this circle a center of 0, 0. When I move the radius slider, as before, you can see it does control the radius of the circle. I'm now going to ask this software to graph h and k as a point, so I can see exactly what that is. When h and k represent the point 0, 0, my circle stays at the origin. Now watch what happens as we adjust the sliders. First we'll move h. When h is +1, the center's at 1, 0. When h is 2, the center is at 2, 0. And when h is 3, the center is 3, 0. Similarly, we can go in the other direction by making h negative. I'll reset h back to 0, and now I'll manipulate k. Watch what happens. You can see the h value shifts the circle horizontally while the k value shifts it vertically. And we can do both things at once. When I let h and k both equal 1, you can see the center is now located at 1, 1. When h and k both equal 2, it's at 2, 2. And my circle is staying the same size because I haven't adjusted the radius slider. This circle has a center of 2, 2, and it's 3 units from the center of the circle to the outside edge. I can move the center of the circle to -4, 5 by moving h to take on the value of -4 and k to take on the value of 5. So what we've just seen is when your center is located at the point h, k and the radius is r, the general equation for the circle will look like this: x minus h, the quantity squared, plus y minus k, the quantity squared, equals the radius squared. Question 1 says, write the standard form of the equation of the circle with the given center and radius. There are 2 general equations for a circle. The first, x squared plus y squared equals radius squared when your center is located at 0, 0 and your radius is r. When your center is located at a different point, this is the correct formula to use. So in this example, because our center is listed as -2, -3, that's a point other than 0, 0. So this is the formula that I'm going to follow to get my equation of the circle. I begin the formula, and when I get to the value of h, I substitute the first coordinate of the center. Now, because it's a -2 and there's a subtraction sign, I'm going to be very careful with how I write that. Quantity squared plus. Now the formula continues, y minus, and when I get to the value of k, I'm going to substitute the y coordinate of my center point, which is again a negative number, so I'm going to be careful. Quantity squared equals, and on the other side of the formula, it's equal to the radius squared. So I would substitute the value square root of 5 squared. Now notice the directions here do indicate we should simplify our answer. We do not typically leave 2 signs sitting next to each other. Subtracting a negative number is always the same as just performing a single addition. The same thing is true for the next part of the formula where we have minus a -3. That's the same as just performing addition of 3. And lastly, squaring and square rooting are opposite operations, just like addition and subtraction. They cancel each other out. When I square the square root of 5, I just get 5. This would be my answer. In addition, you should be able to work a problem like this backwards, where if you were given the equation of a circle, and I'm just going to make one up very quickly, you should be able to identify the center and the radius. Now you have to be very careful here. When we took the value of h, which was a -2, and we simplified it, it ended up switching to +2. Same thing occurs with -3. When we substitute it, because we end up with the double minus sign, it ends up becoming +3. So in other words, when I look at what's in the parentheses, my h value, my coordinate for the center, needs to change signs. Same thing for k, because remember, the center was -2, -3. The same thing is true in my example here. When I want the coordinates of the center, I'm always going to take my h value and sign change what's sitting in the parentheses. So my h value would be -1 for this circle, and I have a -3 sitting here, so my k value I will sign change into +3. And last, remember that this 36 represents the radius squared. So if this is the radius squared, What number do I square to get 36? Well, the radius squared is supposed to equal 36. I can solve for the radius by doing the opposite operation for squaring, which is square rooting on both sides. Square and square root are opposite operations. They cancel out, leaving me with r equals the square root of 36, or in other words, 6. So my answer to this particular question would be that the center has coordinates -1, 3, HK, and a radius of 6. All right, in example 2, we're asked to give the center and radius of the circle described by the equation and then graph the equation. Use the graph to identify the relation's domain and range. And notice it calls it a relation and not a function, because remember, circles are not going to pass the vertical line test. You'll notice I went down below and began writing the version of the circle equation that looks most similar to what I'm given. Right below that, I'm going to write the equation I'm given in this particular example. First thing I notice is that this equation has just x squared, whereas my original circle equation here has x minus h. Well, what is the only value that h can take on that when you subtract it from x, it stays x? This is telling me that h has to be 0. Now, just like the last example, when I need my k value, I'm going to observe what's sitting here after the y, and I'm going to perform a sign change on it. So k would be +3. 25 is the radius squared. So to find out what the radius is, I need to take the square root of 25, and that of course equals 5, which would be my radius. So what I've just determined is that this circle should have a center at the point 0, 3 and a radius of 5 units. When you go to MyMathLab and you need to graph a circle, you're going to click on the graphing tool and follow the directions at the top. Click the graph and choose a tool in the palette. Follow the instructions. In this case, we would be looking to graph a circle. The directions change to say click the graph to plot the center. So whatever point I'd want to be my center, I would click once, and you can see it's holding that position. And then I need to plot a point on my circle. Now let's suppose that this is supposed to be a circle with a radius of 3 units. I'm located at the point 4, 4. So if I want my radius to be 3 units, I would go 1, 2, 3 in any direction, up, down, left, or right. So I can go this direction, but notice I get the same circle if I go to the right. I get the same circle if I go up. I get the same circle if I go down. The only thing I don't want to do is go diagonally, because when you move diagonally, this is actually not 3 units. This is 3 diagonal units, which is different. So when you're drawing your radius, make sure you stay in the 4 main directions, up, down, left, or right. Click that point. And now it gives you one last opportunity to move your circle around if you need to. If you like it where it was, you would click Save. Now, the last part of the question, it asks us to say what the domain is and what the range is. Okay, so please remember, domain is your set of inputs. You are describing your lowest and highest x values. So with regards to the x-axis, that's the point that's furthest out to the left. Here is the point that is furthest to the right. So my interval for the domain is going to be from x is -5 to +5. And we can equal those values. Notice I have colored in points sitting at the edges of the circle. So I would use square brackets to show I can equal this value and this value. And as far as the range goes, you're just turning your attention to the lowest and highest y values. The lowest y value occurs there. The highest y value occurs here. So the correct interval is -2 to 8, including both those values.